Swayam Prabha. Digital India. Educated India.
Once you understood the heuristic technique, now we have to go to the discuss search minimizing the total estimated solution cost. So, the most widely known form of the best first search is called a search, pronounced a star search. It evaluates the nodes by combining G of n, the cost to reach the node, and H of n, the cost to get from the node to the goal. So, this is already we discussed in the graph theory, so that we have to implement here, and then we required f of n is G of n plus H of n, and G of n is a node by combining, and H of is the cost to reach the node. So, G of n gives the path cost from the start node to n, H of n is estimate the cheapest path from n to the goal. So, f of n is the estimated cost of the cheapest solution through n, we can determine with G of n plus H of n. So, thus if we are trying to find the cheapest solution, the reasonable thing to try first the node and the lowest value of G of n plus H of n. So, it turns out that this strategy is more than just reasonable, provided that the heuristic function H of n satisfies certain conditions, that is A star search is both complete and optimal. So, the algorithm is identical to uniform cost search except that A star uses G plus H instead of G. So, this is the already we started to discuss search algorithm. We did initial state where we started with ORAND. This strategy greedy best first tree search for the butcherest with the straight line distance heuristic method, and we denoted with the node of 366 distance. So, after expanding odd to Sibiu, Timizorov and Zerind, and after expanding Sibiu, we have Oran, Fagres, Odia and Rumunsi Vilicia. So, that the expanding Fagras is maps to Sibiu and Bucharest, and once you reached Sibiu, that is a way to search the best free search from odd to Sibiu. So, this is a straight distance method of heuristic, call it as H suffix SLD. So, stages in the greedy best free search. This is the technique we have to use for searching the distance from source to the sink. Now, we are going to identify the condition of optimality, that is called it as the admissibility and consistency. The first condition we require for optimality is that H of n be admissible heuristic, and admissible heuristic is one that never overestimate the cost to reach the goal, because G of n is the actual cost to reach n along the current path, and f of n equal to G of n plus H of n. So, we have as an immediate consequence that f of n never overestimate the true cost of the solution along the current path through n. So, the admissible is a heuristic or by nature, and optimistic because they think the cost of the solving problem is less than the actual is. An obvious example of an admissible heuristic is the straight line distance that we use in getting the Bucharest. Straight line distance is admissible because of the shortest path between any two points is a straight line. So, the straight line cannot be overestimated. The figure 24 we show the progress of A star tree for Bucharest. So, the value of G are computed from the step cost in the figure 3.2, and the value of HLD are given in figure 3.22. Notice in particular the butchers first appears on the frontier at the step E, but it is not selected for expansion because its F cost is higher than that of the Pitesti 417 and F cost is 450. So, another way to say that is that there might be a solution through Pitesti whose cost is as low as 417. So, the algorithm will not settle for the solution of the cost 450. For a second, a slightly stronger condition called consistency, or sometimes it is a monotonicity, is required only for application of A star to a graph search. So, a heuristic h of n is a consistent if for every node n and every successor n dash of n generated by any action A. So, the estimated cost of reaching the goal from n is no greater than the step cost of getting to n dash plus the estimated cost of reaching the goal from n dash. So, h of n is less than or equal to cost h of c of n comma a comma n dash plus the heuristic of n dash also added, so that the step cost can be calculated. That is, heuristic cost is a consistence we can easily find out. So, this is the form of general triangle inequality, which stipulates that each side of the triangle cannot be longer than the sum of the other two sides. So, it is called as a triangular inequality. Here the triangle is formed by n and n dash and the goal Gn closest to n. For an admissible heuristic, the inequality makes perfect sense. If there were a route from n to Gn via n dash that was cheaper than h of n, and that would violate the property of h of n is a lower bound on the cost to reach g of n. So, it is fairly easy to show that every consistent heuristic is also admissible. Consistent is therefore a stricter requirement than admissibility, but one has to work quite hard to concoct a heuristic that are admissible but not consistent. So, all the admissible heuristic we discussed this chapter also consistent. For example, heuristic SLD, we know that the general triangular inequality is satisfied when each side is measured by the straight line distance, and the straight line distance between n and n dash is no greater than c of n comma a comma n dash. Hence, h suffix SLD is a consistent heuristic. So, this is most important for A and ML. Next, optimality. As we mentioned earlier, A star has the following properties. Tree search version of A star is optimal if h of n is admissible, while the graph search version is optimal if h of n is consistent. And second of these two claims, since it is a more useful, the argument is essential mirror the argument for the optimality of the uniform cost search, with G replaced F just as in the A star algorithm itself. So, the first step to establish the following: number 1, if h of n is consistent, then the value of the f of n along any path are non-decreasing. The proof follows directly from the definition of consistency. If you take n dash is a successor of n, then g of n dash equal to g of n plus c of n comma a comma n dash for some action A. So, we have f of n dash equal to g of n dash plus h of n dash. So, which is equal to g of n plus c of n comma a comma n dash plus h of n dash, which is greater than or equal to g of n plus h of n equal to f of n. So, the next step we have to prove that whenever A star is selects a node for n for expansion, so the optimal path to that node has been found. Where this is not the case, there would have been another frontier node n dash on the optimal path from the start node to n. So, by the graph separation, so the property as mentioned here, so initial state R at you have to mention initially you have to take 0, then it is 366. After expanding R at ORAD associated with Sibiu, so that 393 equal to 140 plus 253, and in Timisoara we have a 447 equal to 118 plus 329, where Zerind is 449 equal to 75 plus 374. After expand of Sibiu, we have to go to the 4 subdivision: Orad, Fagres, Oradia and Rumika Vilaya, and Orad is 646 totally now, and it consists of 280 plus 366, and Fagros is 415 equal to 239 plus 176. Oradia is 671 equal to 291 plus 380, and Zuniku Vilayo is 413 equal to 220 plus 193. So, after expanding Remunicua Vilaya, we have some more subdivision, 3 subdivision is Crayonova and Pitasti and Sibiu, and then they have a length of 346 is 280 plus 366, and Fagres is 415 equal to 239 plus 176, and Oradia is 671 equal to 291 plus 380, and Rimitua Vilaya subdivision is Craiova, Pitasti and Sibiu is 526 equal to 366 plus 160, and 470 equal to 317 plus 100, and Sibiu 553 equal to 300 plus 253. After expanding Fagaras, Arad can be subdivision already, Sibiu and Timizora and Zerind, and Sibiu subdivision to Arad, Fagras, Oradio and Rimio Vilaya, and Fagras is subdivision to Sibiu and Bucharest. So, it reaches 450. Already we discussed, and then we expanded how the Fagras is expanded, and here Rimia Vilaya expanded to Crayonova and Pitasti and Sibiu, and it is 160, 100, 253 respectively. After expanding Pitasti, the Pitasti expanded to Bucharest and Craiova and Rimina Vilaya, and it reaches the Fagras to Bucharest in the end, and whereas Pitasti reaches to Bucharest and Craiova and Rimino Vilasi in the distinct. Therefore, this is A star search for Bucharest. So, the nodes are labeled as F equal to G plus H, and the H value or a straight line distance to Bucharest taken from the figure already 3.22, and refer it, so that the best search we can do that. And this is a way we have the map of the contour. The innermost contour is a 380 kilometer, and F is a 400, and F another is 420, with Orad as a state starting state, and having the node given to contour have the F cost and less than or equal to the contour value. So, this can be identified if a taxi driver can operate from starting point to the destination, and if you use the AI, and this you have to pre-defined or inbuilt program decide and do that, and the AI can work. So, mathematically how the best search is helping to find the optimality of the cost as well as the best route. Next, we have the F is non-decreasing along the path, N dash would have been lower F cost and N would have been the selected first. So, from the 2 preceding observation, it follows that the sequence node expanded A star using graph search is in the non-decreasing order of F of n. The first goal node selected, the expansion must be optimal solution, because F is a true cost for goal nodes, and all later goal nodes will be at least as expensive. The fact that F cost are non-decreasing along any path also means that we can draw a contours in the state space. Just like the contour in a topographic map, the figure 3.25 shows that an example inside the contour labeled 400, all the nodes of f of n less than or equal to 400 and so on, because A star expands the frontier node of the lower f cast. So, we can see that and A star search fans out from the state node, adding nodes in the concrete bands of the increasing f cast. So, this is the picture we showed, the 3.25. So, the innermost is 400 and outer is a 420 with R at as the state starting state of f cast less than or equal to the contour value. So, with the uniform cast search, A star search as h of n equal to 0, that is a heuristic. So, the band will be circular around the start state. With more accurate heuristic, the bands will stretch toward the goal state and become more narrowly focused around the optimal path. If C star is the cast of the optimal solution path, then we can say the following: A star expand all the nodes with f of n less than C star. A star might then expand some of the nodes right to the goal tour where f of n equal to C star before selecting a goal node. Therefore, completeness requires that there be only finitely many nodes with the cost less than or equal to C star. So, a condition is that is true if all the step costs exceeding some finite epsilon and if B is a finite. So, notice that A star expands no nodes with f of n greater than C star. So, for example, Timizoro is not expanded in the figure 3.24 even though it is a child of the root. We say that the subtree below the Timizoro is pruned because the heuristic SLD is admissible. The algorithm can safely ignore this subtree while still guaranteeing optimality. So, the concept of pruning, eliminating possibilities from considering without having to extreme them, is important for many areas of AI. So, one final observation is that among optimal algorithm of this type, algorithm that extend a search path from the root and use the same heuristic information, A star is optimal efficient for any given consistent heuristic. That is, no other optimal algorithm is guaranteed to expand fewer nodes than A star. So, this is because any algorithm that does not expand all nodes with f of n is less than C star runs the risk of missing the optimal solution. Thus, A star is search complete, optimal and optimal efficiency among all such algorithm is rather satisfying. Unfortunately, it does not mean that A star is the answer to all our searching needs. So, the catch is that for the most problems, the number of states within the goal tour search space is still exponential in the length of the solution. So, the details of analyzing, the details of the analysis are beyond the scope of this talk, but the basic results are as follows. For problems with a constant step cost, the growth is runtime as a function of the optimal solution. Depth D is analyzed in the terms of absolute error or the relative error of the heuristics. So, the absolute error or delta is identically equal to h star minus h, where h star is the actual cost of getting from the root of the goal and the relative error is defined as epsilon is identically equal to h star minus h by h star. So, the complexity results depends very strongly on the assumption made about the state space. So, simplest model studied in the state space as a single goal and is essentially a tree with a reversible action. So, the 8 puzzles satisfy the first and third of the assumption. So, in this case the time complexity of A star is exponential in the maximum absolute error, that is order of b power delta for constant step cost. So, we can write this as order of b power epsilon d, where d is the solution depth. For almost all heuristic in practical use, the absolute error is at least proportional to the path cost h star. So, epsilon is constant or growing and the time complexity is exponential in d. So, we can also see the effect of the more accurate heuristic order of b power epsilon d equal to order of b power epsilon whole power d. So, the effective branching factor is B epsilon is finally conclude. Now, when the state space has a many goal states, particularly near optimal goal states, the search process can be led astray from the optimal path, and there is an extra cost proportional to the number of goals whose cost is within the factor epsilon of the optimal cost. Finally, in the general case of the graph, the situation is even worse. There can be exponentially many states with f of n less than epsilon c star, even if the absolute error is bounded by the constant. For example, consider the version of the vacuum world where the agent can clean up any square for unit cost without even having to visit it. In that case, squares can be cleaned in any order. With n initially dirty squares, there are 2 power n states where some subset has been cleaned and all of them are on optimal solution path and hence satisfy f of n less than c star, even if the heuristic has an error of 1. So, the complexity of A star often makes it impractical to insist on finding an optimal solution. One can use the variance of A star that to find a suboptimal solution quickly, or one can sometimes design heuristic that are more accurate but not strictly admissible. In any case, the use of good heuristic still provides enormous savings compared to the use of a uninformed search. So, the best search algorithm is find function of a recursive best first search and return a solution, or failure once again the algorithm for recursive best first search is function recursive best first search problem returns a solution or failure and returns RBFS recursive best first search, and the problem make a node and initial stage required. If not, you put infinity, and the function of RBFS, that is recursive best first search problem, is a node f limit returns a solution or failure and a new f cost limit. If problem goal test node state, then return solution node and put a successor and put a bracket like this for each action in problem action node state. Do add child node problem node action into successor. If successor is empty, then return failure, otherwise put infinity. For each s in successor, do update f with the value from previous search if any. S dot f the maximum s dot g plus s dot h comma node dot f, and loop do the lowest f value node is in successor, best dot f greater than f limit, then return failure, and alternative the second lowest f value among successor, result the best dot f is RBFS recursive best first search of the problem comma best comma minimum of f limit comma alternative. So, if your result is not equal to failure, then return result. So, this is the inbuilt algorithm for the recursive best first search ideas. Next one is a memory bound heuristic search. This is the simplest way to reduce the memory requirement for A star is to adopt the idea of interactive deepening the heuristic search context. So, this is the once again the simplest way to reduce the memory requirement for A star is adapt the idea of iterative deepening to the heuristic search context, resulting in the iterative deepening A star algorithm. The main difference between IDA and the statement iterative deepening is that cutoff used is the f cost g plus h rather than the depth at the each iteration. So, the cutoff value is the smallest f cost of any node that exceeded the cutoff on the previous iteration. So, the IDA is a practical, right, and then IDA is a iterative deepening A star, and then it's a practical, and it is a recursive best first search is a simple recursive algorithm that attempt to mimic the operation of a standard best first search, but using only a linear space. The algorithm shown in the figure 26, its structure is similar to the recursive depth first search, but rather than continuing indefinitely down the current path, it uses the f limit variable to keep the track of the f value of the best alternative path available from any ancestor of the current node. If the current node exceeds the limit, the recursive unwinds back to the alternative path. As the incursion unwinds, the RBFS replaces the f value of each node along the path with a backed up value, the best f value of its children. In this way, the recursive best first search remembers the f value of the best leaf in the forgotten subtree and can therefore decide whether it is worth re-expanding the subtree at the later time. So, the figure 27 shows that RBF reaches Bucharest. So, this is the picture of the tree shows that the shortest route to Bucharest, and f value for each recursive call shown in the top of each current node, and every node is labeled with f cost. So, the path through Rimincia Villania is followed until the current best leaf Pitasti, and the best leaf value of the forgotten subtree as described is back to the Rimincia Villacea. Then best leaf value of the forgotten subtree is backed up to the Fagres. Then Rimincia Villacea is the expanded the time because the best alternative path cost at least 447. So, this is the expansion continues to Bucharest. So, this is the demonstration of the figure, the expanded of R at Sibiu and Rimiu Villacea, and after unwinding back to Sibiu and expanding Fagres, after switching back to Rimincia Villacea and expanding Vitesse, we reached this three state like this. So, this is the way we can search for the RBFS of the f shortest route for the f cost of the Bucharest. Next, learning to search better. So, we have presented several fixed strategies called it as a breadth first, greedy best first, and so on. So, that have been designed by the computer scientist. Could an agent learn how to search better? So, the answer is yes. The method rests on an important concept called it as meta level state space. Each state in the meta level state space captures the internal computational state of the program, that is searching in the object level state space such as Romania. For example, the internal state of the A star algorithm consists of the current search tree. Each action in the meta level state space is a computation step that alters the internal state. For example, each computation step in A star expands the leaf node and adds its successor to the tree. Thus, the figure 24 which shows the sequence of larger and larger search trees and can be seen depicting a path in the meta level state space where each state on the path is an objective level search tree. So, now the path in the figure 24 have 5 steps, including one step, the expansion of Fagres, that is not especially helpful. For harder problems, there will be many such missteps, and a meta level learning algorithm can learn from these experience to avoid exploring unpromising subtrees. So, the techniques used for this kind of learning is described. The goal of the learning to minimize the total cost of the problem solving, trading of computational expansion and path cost. So, one may refer this book, you can understand the meta heuristic level also can find the path of the cost. Now, we have a heuristic function. So, we have a 8 puzzle was one of the earliest heuristic search problem as mentioned in the section. So, object of a puzzle is slide the tiles horizontally or vertically into empty space until the configuration of matches the goal conformation or configuration. So, the goal for configuration picture in the 3.28, this is the solution in a 26 steps long. So, the average solution cost for randomly generated 8 puzzles instance is about 22 steps. So, the branching factor is about 3. When the empty tile is in the middle, 4 moves are possible. When it is in the corner 2 and when it is along an edge 3. So, this means that an exhaustive tree search to depth 22 would look at about 3 power 22 is approximately equal to 3.1 to 10 power 10 states. So, a graph search would cut this down by the factor of about 1,70,000 because only 9 factorial by 2 equal to 1,81,440 distinct states are reachable. And see the exercise 0.4. So, this is a manageable number, but the corresponding number for the 15 puzzle is roughly 10 power 13. So, the next order of business is to find the good heuristic function. If we want to find the shortest solution by A star, we need a heuristic function that never overestimate the number of steps to the goal. There is a long history of such a heuristic for the 15 puzzle. Here are 2 commonly used candidates. H1 equal to number of misplaced tiles. So, the figure 3.28 is a typical instead of 8 puzzles. All the 8 tiles are out of position. So, start the state would have a H1 equal to 8. H1 is admissible heuristic because it is clear that any tile that out of the place must be moved at least once, and H2 is the sum of the distance of the tiles from their goal position because tiles cannot move along the diagonals. The distance we will count is sum of the horizontal and vertical distances. This is sometimes called a city block distance or a Manhattan distance, and H2 is also admissible because any move can do in move one tile one step closer to the goal. The tiles 1 to 8 to start the state give a Manhattan distance of H2 equal to what 3 plus 1 plus 2 plus 2 plus 2 plus 3 plus 3 plus 2 equal to 18. So, an expected neither of these estimates the true solution cost, which is 26. So, one way to characterize the quality of the heuristic is effective branching factor B star. The total number of nodes generated by A star is a particular problem is n and the solution depth is d. Then B star is a branching factor that uniform tree of the depth d would have to have in order to contain n plus 1 nodes. Thus, n plus 1 equal to 1 plus B star square and so on. B star whole power d is a polynomial of B star of a degree d. For example, A star finds the solution at the depth of 5 using 52 nodes, then the effective branching factor is 1.92. So, the effective branch factor can carry across problem instances, but usually it is a fairly constant for sufficiently hard problem. Therefore, the experimental measurement of B star on the small set of problems can provide a good guide to the heuristic overall usefulness. So, well designed heuristic would have the value of B star close to 1. So, allowing fairly large problem to be solvable at a reasonable computational cost. So, this is the existence of effective branching factor follows from the result mentioned earlier. The number of nodes expanded of A star growth exponentially with the solution depth. So, the test the heuristic function H1 and H2, we generated 1200 random problems with a solution length from 2 to 24, 100 for each even number, and solved them with iterative deepening search with A star tree search using both H1 and H2. So, the figure 29 gives the average number of nodes generated by each strategy and the effective branching factor. The result suggests that H2 is better than H1 and is for better than using iterative deepening search even for a smaller problem with d equal to 12. A star with H2 is 50,000 times more efficient than uniform iterative deepening depth or deepening search. So, the corresponding So, the corresponding search cost and effective branching factor is designed here. This is a comparison of search effective and effective search branching, and this is a iterative deepening search, call it as IDS. So, IDS stands for iterative deepening search, and A star is algorithm of H1, H2, and data are average over 100 instances of 8 puzzles for each various solution of D. For D2, then we have a iterative deepening search is 10, and A star is algorithm search, it goes to 6, and another way of finding the H2 is A star is 6 will come. Like that you have to do for search cost, whereas effective branching factor it goes to 2.45 for IDS, and A star H1 is 1.79, A star H2 is 1.79. Proceeding in this way for 4, 6, 8, 10 and so on 24, and we have a no value from the IDS from 14 to 24, whereas we have a star of H1 have a data. So, this is a various solution of the length D can be calculated, and we have a search cost as well as effective branching factor also determined, and this is a comparison of what cost of both factors, and data are averaged over 100 instances, and length also what calculated. So, on the might ask whether H2 is always better than H1. So, answer is essentially yes. It is easy to see from the definition of the two heuristic that for any node n, H2 of n is greater than or equal to H1 of n, we say that H2 dominates H1. So, the domination translates directly into efficiency. So, A star is using H2 will never expand more nodes than A star using H1. So, we accept possibly for some nodes with Fn equal to C star. The argument is simple. Recall the observation on this book page number 70 that every node of f of n is C star will surely be expanded, and this is the same as saying that every node with h of n is less than C star minus g of n will surely be expanded, because H2 is at least as big as H1 for all nodes. So, every node that is surely expanded by A star search with H2 will also surely be expanded with H1, and H1 might cause other nodes to be expanded as well. Hence, it is generally better to use heuristic function with higher values, provided it is consistent and that the computation time for the heuristic is not too long. So, next we have to discuss the generating admissible heuristic from relaxed problem. We have seen that both H1 and H2 are fairly good. The heuristic for the 8 puzzles and H2 is better. How might one have come up with H2? Is it possible for the computer to invent such a heuristic mechanically? H1, H2 are estimates of the remaining path length of 8 puzzle, but they are also perfectly accurate path length for simplified version of the puzzle. If the rules of the puzzle were changed so that tile could move anywhere instead of just to the adjacency empty square, then H1 would give the exact number of the steps in the southeast solution, or sorry, H1 would give the exact number of steps in the shortest solution. Similarly, if a tile could move one square in any direction even onto an occupied square, then H2 would give the exact number of steps in the shortest solution. So, a problem with fewer restriction on the action is called relaxed problem. So, the state space graph of the relaxed problem is a super graph of the original state space, because the removal of restriction creates added edges in the graph were changed so that the tile could move from anywhere instead of just to the adjacent empty square. Then H1 would give the exact number of steps in the shortest solution. So, similarly, if a tile could move one square in any direction even onto an occupied square, then H2 would give the exact number of steps in the shortest solution. So, a problem with fewer restriction on the action is called relaxed problem. So, the state space graph of the relaxed of the super graph of the original state space because the removal restriction create added edges in the graph. So, because the relaxed problem of adds edges to the state space, any optimal solution in the original problem is also a solution in the relaxed problem, but the relaxed problem may have a better solution. The added edges provide shortcuts, hence the cost of the optimal solution to a relaxed problem is an admissible heuristic for the original problem. Further, because the derived heuristic is an exact cost for the relaxed problem, it must obey the triangle inequality and is therefore consistent. So, if a problem definition is written down in a formal language, it is possible to construct relaxed problem automatically. For example, the 8 puzzle action are described as a tile can move from square A to square B if A is horizontally or vertically adjacent to B and B is a blank. So, we can generate 3 relaxed problem by removing one or more or one or both of the condition. Number 1, a tile can move from square A to square B if A is adjacent to B. A tile can move from square A to square B if B is a blank. A tile can move from square A to square B. So, from A we can derive H2. The reasoning is that H2 would be the proper score if we moved each tile in turn to its destination. So, the heuristic derived from B is discussed. So, we can derive H1 misplaced tile because it would be proper score if tiles could move to their intended destination in one step. Notice that it is crucial that the relaxed problem generated by this technique can be solved essentially without search, because the relaxed rules allow the problem to be decomposed into 8 independent subproblems. The relaxed problem is hard to solve, then the values of the corresponding heuristic will be expensive to obtain. So, a program called Absolver can generate a heuristic automatically from problem definition using the relaxed problem method and various other techniques. So, Absolver generate a new heuristic for the 8 puzzle that was better than any pre-existing heuristic and found the first useful heuristic for the famous Rubik cube puzzles. So, one problem with generating new heuristic function is that one often fails to get a single clearly best heuristic. If a collection of admissible heuristic H1 to Hm is available for a problem and none of them is dominates to any of the others, we choose. As it turns out, we need not make a choice. So, we can have the best of all worlds by defining H of n equal to maximum of H1 of n to Hm of n. So, this is the the 8 puzzles instances. So, this way we can move that if it is a free. So, the task is to get the tiles 1, 2, 3 and 4 into their correct position. So, without worrying about the happens to the other tiles, and this composite heuristic uses whichever function is most accurate. On the node is a question because the component heuristic are admissible and H is admissible. It is also easy to prove that H is consistent. Further, H dominates all of its components heuristic. So, next is generating admissible heuristic from subproblem and this based on the pattern databases. So, admissible heuristic can be derived from the solution of the subproblem of the given problem. So, in figure 30 shows the subproblem of the 8 puzzle instance. The subproblems involve getting tiles 1, 2, 3, 4 into their correct positions. Clearly, the cost optimal of the subproblem is lower bound on the cost of the complete problem. It turns out to be the more accurate than Manhattan distance in some cases. So, the idea behind pattern databases is to store these exact solution cost for every possible subproblem instance in our example. So, every possible configuration of the 4 tiles and the blank, then we compute an admissible heuristic HDB for each complete state encountered during a search simply by looking up the corresponding subproblem configuration in the database. So, the database itself is constructing by searching back from the goal and recording the cost of each new pattern encountered. The expense of this search is modernized over many subsequent problem instances. So, the choice of 1, 2, 3, 4 is fairly arbitrary. So, we could also construct the databases 5, 6, 7, 8 for 2, 4, 6, 8 and so on. So, each database yields an admissible heuristic, and these heuristic can be combined and explained earlier by taking the maximum value. So, a combined heuristic of this kind is much more accurate than the Manhattan distance. So, the number of nodes generated when solving random 15 puzzles can be reduced by a factor of 1000. So, one might wonder whether the heuristic obtained from 1, 2, 3, 4 database and the 5, 6, 7, 8 could be added. Since the two subproblems seems not to overlap, would this still give an admissible heuristic? So, answer is no, because the solution of 1, 2, 3, 4 subproblem and the 5, 6, 7, 8 subproblem for a given state will almost certainly share some moves. So, it is unlikely 1, 2, 3, 4 can be moved into place without touching 5, 6, 7, 8 and vice versa. But what if we do not count those moves? That is, we record not the total cost of solving 1, 2, 3, 4 subproblem, but just the number of moves involving 1, 2, 3, 4. Then it is easy to see that the sum of the two costs is still a lower bound on the cost of the solving the entire problem. So, this is the idea behind disjoint pattern databases. With such databases, it is possible to solve the random 15 puzzles in the few milliseconds. So, number of nodes generated is reduced by the factor of 10,000 compared with the use of the Manhattan distance. For 24 puzzles, a speed up of the roughly factor of 1,000,000 can be obtained. So, the disjoint pattern databases work for sliding title puzzles because the problem can be divided up in such a way that each move affects only one subproblem, because only one tile is moved at a time. For a problem such as a Rubik cube, this kind of a subdivision is difficult because each move affects 8 or 9 of the 26 cubics. More generally, ways of defining additive admissible heuristic have been proposed to apply the Rubik cube, but they have not yielded a heuristic better than the best non-additive heuristic for the problem. So, learning heuristic from experience. So, heuristic function h of n is supposed to estimate the cost of the solution beginning from the state at a node n. How could an agent construct such a function? So, one solution was given in preceding section, namely to devise the relaxed problems for which an optimal solution can be found easily. Another solution to learn from experience. Experience here means solving lots of 8 puzzles for instance. So, each optimal solution to the 8 puzzle problem provides example for which h of n can be learned. Each example consists of the state for the solution path and the actual cost of the solution from that point. From these examples, your learning algorithm can be used to construct a function h of n that can with the luck predict solution cost for other states that arise during search. Techniques for doing just this using neural net, decision trees and other methods are demonstrated in this chapter. So, this is the reinforcement learning method described in the chapter also applicable. So, the inductive learning methods to work best when supplied with features of the state that are relevant to predicting the state value rather than with just raw state description. So, the inductive learning method work best when supplied with features of the state that are relevant to predicting the state's value rather than with just a raw state description. For example, the future number of a misplaced tile might be helpful in predicting the actual distance of the state from the goal. So, let us call this future x1 of n. We could take 100 randomly generated 8 puzzle configurations and gather statistics on their actual solution cost. So, we might find that xn of n is 5. So, the average solution cost is around 14 and so on. Given these data, the value of xn can be used to predict h of n. Of course, we can use several features. The second feature is x2 of n, might be number of pairs of adjacent tiles that are not adjacent in the goal state. How should x1 of n and x2 of n can be combined to predict h of n? And a common approach is to use the linear combination h of n equal to c1 into x1 of n plus c2 of x2 of n. The constant c1 and c2 are adjusted to give the best fit to the actual data on solution cost. One expects both c1 and c2 to be the positive because the misplaced tiles or incorrect adjacent pairs make the problem harder to solve. Notice that this heuristic does satisfy the condition that h of n equal to 0 for goal states, but it is not necessarily admissible or consistent. So, we have a summary. This talk has introduced method that an agent can use to select action in environments that are deterministic, observable, static and completely known. In such a cases, the agent can construct sequence of actions that achieve its goal. So, this process called search. Before an agent can start searching for solution, a goal must be identified and a well-defined problem must be formulated. A problem consists of 5 parts: initial state, set of action, transition model, and describing the result of those action, goal state function, path cost. So, these are all the 5 paths. The environment of the problem represented by the state space. A path through the state space from the initial state to goal state is a solution, and we need a search algorithm treat the states and action as atomic. They do not consider any internal structure they might possess. A general tree search algorithm considers all possible paths to find a solution, whereas graph search algorithm avoids consideration of redundant paths. Search algorithms are judged on the basis of completeness, optimality, time complexity and space complexity. Complexity depends on B. So, the branching factor in the state space, and D, the depth of the shallowest solution. So, uniform search method have access only the problem definition. So, the basic algorithm are as follows. One is breadth first search, expand the shallowest nodes first. It is a complete optimal for unit step cost, but has exponential space complexity. Next is uniform cost search, expand the node with the lowest path cost g of n and is optimal for general step cost. And third one is depth first search, expands the deepest unexpected node first. It is neither complete nor optimal, but has a linear space complexity. Depth limiter search adds an depth bound. Iterative depending search calls a depth first search with increasing depth limit until a goal is found. It is complete optimal for unit step cost as a time complexity, and comparable to breadth first search and has a linear space complexity. Bidirectional search can enormously reduce time complexity, but it is not always applicable and may require too much space. And informed search method may have access to heuristic function h of n that estimate the cost of the solution from n. The generic best first search algorithm selects a node for expansion according to evaluation function. Greedy best first search expands the nodes with minimal h of n, and it is not optimal but is often efficient. A search expands nodes, A star search expansion nodes with the minimal A star search expansion nodes with minimal f of n equal to g of n plus h of n. A star is a complete and optimal provided that h of n is admissible for tree search, for consistent, for graph search. A space complexity of A star is still prohibitive. RBF, yes, recursive best first search and simplified memory bound A star are robust. Optimal search algorithm that use limited amounts of memory given enough time. They can solve problems that A star cannot solve because it runs out of memory. The performance of a heuristic search algorithm depends on the quality of the heuristic function. One can sometimes construct a good heuristic by relaxing the problem definition, by storing a pre-computed solution cost for subproblems in a pattern database, or by learning from experience with the problem class.